In section 7.1, day 2, we're going to continue to look at sampling distributions. After this lesson, you should be able to define a sampling distribution, distinguish between population distribution, sampling distribution, and distribution of sample data, determine whether a statistic is what's known as an unbiased estimator of a population parameter, and describe the relationship between sample size and the variability of our estimator. To take a look at a sampling distribution, here's an example. We could take a handful of different samples of 20 colored chips, and we're looking to see what proportion would be red. There are many possible simple random samples of size 20 from a population of size 200 that we could take. If we took every one of those possible samples, calculated the sample proportion for each, and graphed all of those, we'd have what's known as the sampling distribution. Definition of sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In practice, it's difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process of taking many samples. One of the uses of probability theory in statistics is to obtain a sampling distribution without doing this simulation. We'll get to that theory later. There are actually 3 distinct distributions involved when we sample repeatedly and measure a variable of interest. The first is the population distribution, and it gives us the values of the variable for all individuals in the population. Again, when we're doing inference, this is unknown. 2. The distribution of sample data shows the values of the variable for all individuals in the sample. And 3. The sampling distribution, which shows the statistical values of all possible samples of the same size from the population. So here's an example with the looking for the chips. I've got my population distribution, and you can see I have 100 blue and 100 red actually in my population distribution. So my parameter, or p, is 0.5. If I continue to take a simple random sample of size 20, you can see my first simple random sample of size 20 yields 8 out of 20, or 0.4, as my sample statistic p hat. My second simple random sample yields 11 out of 20, which is 0.55. Again, that's a statistic. Simple random sample, the third one I had, is n is equal to 20, and I got 13 out of 20, which is 0.65. If I were to do this repeatedly and graph the proportions that were obtained through these many trials of simple random sampling, I would have what's known as my sampling distribution. And those are for my p hats, which I'm trying to use to estimate my population parameter p. The fact that statistics from a random sample have a definite sampling distribution allow us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider the center, shape, and spread of the distribution. In the chip example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? Note that the center of our sampling distribution of approximately all the samples is close to 0.5. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 0.5. This leads to a definition. A statistic used to estimate a parameter is known as an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. That is a good thing. That is what we want to have. We do not want to have what's known as a biased estimator. Looking at spread, get a trustworthy estimate of an unknown population parameter. Start by using a statistic that's an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator does not guarantee that the value of your statistic will be close to the actual parameter value. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimator close to the true value of the parameter, as you can see from above, taking a sample of 100 versus a sample of 1,000. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger sample sizes give a smaller spread. The spread of a sampling distribution does not depend on the size of the population, as long as the population is at least 10 times as large as the sample. We can think of the true value of a population parameter as a bullseye on a target, and of a specific statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. Take a look at the 4 bullseyes below. In bullseye A, our arrows were very tightly bunched, but they were very far from where the population parameter actually is. Again, you must think as the bullseye as the population parameter. In B, my arrows are very spread apart, but they are all centered around my population parameter. In C, the arrows are pretty well spread apart, and they are all far away from my population parameter. And D, they are all clustered together and very centered right around the bullseye. Bias again means that our aim is off and we consistently miss our bullseye in the same direction. Our sample values do not center on the population value. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give us similar results. The lesson about center and spread is clear. Given a choice of statistics to estimate an unknown parameter, choose the one with no or low bias and minimal variability. From our targets to the left, again, D is the best. It has no bias because it's all centered around the bullseye, and low variability because the shots are not spread apart. The second best would be B because they have low bias. They are still centered all around the population parameter, the bullseye, even though they are highly spread. Followed by A and C. Sampling distributions can take on many shapes. The same statistic can have sampling distributions with different shapes depending on the population distribution and the size of the sample. Be sure to consider the shape of the sampling distribution before doing inference. Here are 5 different graphs of a sampling distribution. Sampling distributions from different statistics used to estimate the number of German tanks in a German tank problem. The blue line represents the true number of tanks. Note the different shapes the estimators took on. Which statistics gives the best estimator, and why? Again, remember you're looking for the one that has the low or no bias, and then from there has the least variability. As a review of section 7.1 and sampling distributions, you need to remember the difference between parameters and statistics. A parameter is a number that describes a population. To estimate an unknown parameter, we use a statistic calculated from a sample. The population distribution of a variable describes the values of the variable for all individuals in the population. The sampling distribution of a statistic describes the values of a statistic in all possible samples of the same sample size from that same population. A statistic can be an unbiased estimator or a biased estimator of a parameter. Bias means the center or the mean of the sampling distribution is not equal to the true value of a parameter. If it is equal to the mean, it would be an unbiased estimator. The variability of a statistic is described by the spread of its sampling distribution. Larger samples will give you smaller spread. And when trying to estimate a parameter, choose a statistic with low or no bias and minimize variability. Don't forget to consider the shape of the sampling distribution before doing inference. This is the end of section 7.1. In section 7.2, we'll continue to look at sampling distributions and we'll turn our focus to proportions.